Hi everybody, this is Brendan and this is 30 Days of Solidity, and this is for day 9 on the challenge calendar called Smart Calculator. This is a smart contract where essentially you will have one smart contract calling another smart contract, invoking its functions, and also I guess is a way to demonstrate an early or primitive version of proxy smart contracts where one smart contract can invoke another and then change the underlying implementation to use a different implementation or a newer version, but still have the same base smart contract. And the way that we'll accomplish all of this is using interfaces, right? So we'll get to the interfaces in a bit, but essentially we will have, let's copy the manager and only manager from the previous smart contract tip jar. Let's just implement that, close, and don't need either of those. So in the constructor we set a manager and then there's an only manager in the constructor, right? Sorry, an only manager modifier which will be used in other functions. Right, so then we can do something called calculate, right? That's the main function that the user is supposed to call, invoke each time. Now, public view and returns uint 256, right? Worth noting that in Solidity you don't really have numbers with decimal places or rational numbers, or irrational numbers for that matter. You just have whole numbers, right? And you basically represent everything that you need using uint 256. So that's the reason that everything is denominated in way within Solidity, and if you want to get the actual value of the cryptocurrency, then you just have to multiply it by 10 to the power of the number of decimal places. For example, 10 to the power of minus 18 if you're using way with Ether. And that's the same for most other EVM-based projects, but not necessarily all of them. Okay, so anyway, we will define a calculate function. Now, if we want to use an interface to invoke another smart contract, right? We don't want to have to keep modifying this interface whenever the interface of the other smart contract changes. So for that reason, let's not have separate methods for add, divide, and so on and so forth, right? All the different mathematical operations that a calculator will support. We'll just use a string and then call that method. And then the inputs will be a dynamic array. So that will be uint 256 with these square brackets. And because it's dynamic, we put the keyword memory, and then we'll call that numbers, right? So this is fairly flexible, flexible enough to represent calculator operations, because we have a method, and then we have a dynamic array of uint 256. So you can have any number of numbers that you like, and then there's also and it'll return a number, right? And so what we could do is we could say if method is, I'm just using pseudocode here, is add, then return numbers 0 plus numbers 1. Now, this is not going to work for a couple of reasons. You can't compare strings inside of Solidity like this, right? You can't use equals either. It doesn't work because Solidity doesn't have that operator. So we have, but this is the idea, right? This is basically the idea. Like we'll have a bunch of if statements with returns of that. But the thing is, we are not going to do that inside of this function, right? Inside of this smart contract. We are going to define an interface for the same calculate function and then invoke that instead. And we will have another function for update calculator implementation and store a deployed version of that smart contract here. So let's go ahead and do that. So we'll create a new file and I will call it iCalc.sol, and let's copy this and paste it, close, right, and let's see. I think I'll only want to keep the pragma, and then I'll say iCalc like that, and say interface for all calculator implementations used by smart calculator, right? All right, and we'll call this iCalc, but instead of contract, we're going to call it interface. So this is crucial, right? So that once you type the word interface, right, let's undo that, right? So you can see this is all valid. But once you say interface, then it has a problem with everything, right? Because you can't have implementations inside your interfaces, right? And one more thing needs to change, which is that interface methods cannot be public, they need to be external. And what external means is it's the same as a public smart contract visibility modifier for a function, but the difference is that when it's public, that can be called from an account, like for example a wallet, or it can be called by another smart contract, whereas external can only be called, I believe, by an account, right? If it were in a smart contract, but I'm not sure exactly why, but when you define an external in an interface, then you can, the implementation of that can be called by the external. Not exactly sure how that works, but it is what it is. All right. Let's see. Okay, so I've got my interface, and now I need an implementation of iCalc before I can start using that in Smart Calculator. So I'm just going to create a new file called calc_v1, and I'm going to make this intentionally not a full implementation, right? I'm going to I'm going to hold it back essentially. So let's delete that, and the calc_v1 will be a first, not very good implementation for of iCalc for smart calculator. All right, so let's call that calc_v1, and I'm going to get rid of everything. And for this, I need to do import iCalc.sol. That's right. Yeah, let's do it here. Import iCalc.sol. So I've imported the Solidity file for the interface, and then I can say now is iCalc. So I'm telling the compiler that this smart contract needs to implement the interface defined in iCalc, which is this. So that means I need to define a calculate function. So let's go ahead and copy that, right? I know it's almost the same, but and then here's my implementation, right? All right, so the next thing, I can get rid of this. The next thing that I'll do is I will do that if statements that I mentioned earlier on. Are strings equal method and add, right? So I'm about to define the strings equal method, but I'm just sort of using it as pseudocode for the moment. So I'll perform a require and say numbers dot length equals 2, and if it's not 2, it says add only allows 2 parameters. Alright, and then I will say turn numbers 0 plus numbers 1. And I can do the same thing with another if statement, our strings equal subtract. And this will be negative. Alright, and I know I should have another one here because these are unsigned integers. So if number 0 is say 3 and number's 1 is 4, 3 minus 4 will result in an arithmetic underflow. So that is not representable using unsigned integer, and that is bad, right? But I'm intentionally leaving that in for now, right? And then finally, I'll put a require statement for false, so this require statement will always fail, and I'll say unsupported method. Alright, now let's define our strings equal. So function our strings equal string memory A, string memory B, and turns bool. Alright, returns bool, and then this is slightly complicated, but essentially the best way to do string comparisons is to use the raw bytes for them. So bytes a dot length equals to bytes b dot length, and let's get rid of the length. Sorry, this should be public pure, right? And pure is the same as view, except that it doesn't access any methods or state variables. Sorry, it doesn't access any state variables within the same smart contract. So it's can be done purely without accessing state. So that gives you some gas optimizations. So I can't do bytes comparison either. So I'll do a hash, right? And the hash function is kachak or kachak. I'm not sure how to pronounce it. Right. What's this complaining about? Alright, I guess this can be pure. Right. Yeah, so this can be pure as well. Yeah, because we're not accessing any local state. Alright, so our strings equal will essentially find if the strings are have the same number of bytes each, i.e. they have the same length, string length, and then it will also compute the hash of both of the strings. And if the hashes are equal as well, then the strings are equal. And of course, like, this is technically redundant, but it apparently is more gas optimal because it takes longer. If it takes longer, it's more computation intensive to hash than to just look at the length. All right, so that's the Calc v1 implementation. So how do we actually use this, right? So we can go back to iCalc, right? And this is a valid implementation, and we can check that by doing a compile, and we can see this warning for unnamed. There's no compiler error, right? We do see one warning, and it's because essentially the compiler doesn't know that it is not impossible to return a value. So that's what the warning is about. But we know for a fact that as long as each of the if statements here has a return, and at the end of it the require will always revert, there will never be a scenario where we return and there is no return value, right? It's just not possible. But the compiler isn't able to make that same judgment, and that's why there's a warning here. Nevertheless, it is a warning, so we can safely ignore it, having verified that what we just verified. So now Calc v1, if I'm able to compile it without any error, as we can, that means that iCalc has been satisfied successfully, right? So let's go back to Calc v1. All right, so then let's go to Smart Calculator, and now we can use Calc v1, right? But we will not use Calc v1 directly. We'll use iCalc. So import /iCalc.sol, and so Smart Calculator should now add a new function for update calculator that is only executable by the manager. So function update implementation public only manager, and then we can say calculator implementation is equal to new implementation, which will pass in as a parameter. So new implementation is this, right? But instead of passing in as an address, right, which will result in this, which will result in some issues, we'll pass it in as iCalc, because we want to set iCalc as the type. iCalc public calculator import. So the actual slot here in memory or in persistent storage for Smart Calculator will be an address, but within compile time, the auxiliary compiler knows to treat this address, the implementation present within this address, as an instance of iCalc, right? So right now it's empty. Right, so calculator impl is equal to new impl, and that is successfully compiled. We do, however, want to make sure that it is valid. Right, require address new impl. So the address of the new implementation is equal to not equals to address 0x00, right? The null address. Calculator implementation cannot be null address. Right, so let's set that. All right, so that's the update implementation, and then so once we have that, right, inside of calculate function, we can do this, right? We can say return calculator implementation dot calculate method numbers. So this method essentially is just proxying to the implementation, which will be iCalc, an instance of the iCalc interface, which in this case will be calc v1, right? As long as calc v1 is first deployed and then called into update implementation. So in order to make sure that there is actually an implementation, let's use a require address of calculator implementation. Is not null, right? And then we'll say no calculator implementation set, right? All right, so I think that should do it. Let's compile this smart contract. That's fine. All right, let's go this one. Right, let's go deploy this. All right, we'll deploy the smart calculator. And now, let's perform a calculation, and we know it won't work, right? So let's do add, and then we'll pass in, let's see, 1, 2, call, length, sorry. So to pass in a dynamic array, you need to do it like that. So let's try and say 1 plus 2, but it'll say no calculator implementation set. That's fair enough, because in the constructor we've set who the manager is, but calculator impl is essentially it's essentially null, right? So this test will fail for obvious reasons. It is address 0. So now we need to update the implementation, right? So now we need an address for that. So let's go to calc v1. We can't deploy the iCalc, by the way. There is no implementation. There's nothing to deploy. But when we do calc v1, we have an implementation of the iCalc interface. So this is, let's see, calc v1, and let's press deploy. All right. So now we have a calc v1, right? And of course we can do calculate if we want. So we can say, add, and then here we can say 5, 6, let's just say, and we should get a value of 11. But that's calling the implementation directly, right? But that's not what the user is going to do. We're going to use smart calculator instead, right? And so just to recap, if I press add here, we'll get a revert because there's no calculator implementation. Now I'll do add implementation and set the new implementation to the address, the deployed address of calc v1, and press transact. All right, so that was successful. And now if we call add again, we get a value. We can do subtract, right? And 1 minus 2 with unsigned integers will result in an underflow, right? Let's try 1 subtract 1, and that will get us a value of 0. But let's say we do 1 subtract 2, we're expecting a revert, right? And note that there is no detail here, right? There is no detail here about why it errored, because we didn't do a revert with a named thing. This is just a lower level error within the Ethereum virtual machine because of an underflow, and you just get a generic revert, right? The transaction failed, and it just says some generic reason which is what it states for every single time there is a revert. Okay, so what is the point of having a smart calculator and having a calc v1, right? That seems redundant. But the answer is that we can have a second implementation and switch the underlying implementation. So let's go ahead and create one. So let's create a new file called calc v2.sol, and here we go. So calc v1, I'm just going to copy paste that, and this one will be named calc v2, right? R strings equal can remain the same, and calculate, this is where we're going to make our changes, right? So firstly, we're going to solve that require error, right? So this will have an additional rule which will say numbers 0 is if number 0 is more than or equals to numbers 1, right? So if I do that, that means that it'll say, it'll say, basically says, hang on, it should say subtract, subtract these numbers will underflow, right? All right, so then at least we know that it's an underflow. All right, let's try another one, right? So let's do multiply and divide as well, right? So we'll add more methods. So multiply and divide. All right, so this one, the second parameter, right, cannot be 0. Right, so divide doesn't allow a 0 divisor. So we'll just change the actual. So adds the numbers, subtracts the numbers, multiplies the numbers, and divides the numbers. And all of them have a rule for only allowing 2 parameters, which could be different if there's unary or ternary operations, for example, in further implementations, but we don't need to go there for now. And then there is also additional rules. So this is new for subtract compared to V1. So this time when you try to subtract a larger number from a smaller number, it'll basically tell you that that's not allowed. Same goes with divide. If you try to divide a number by 0, then it'll give you an error saying 0 divisors are not allowed. All right, let's compile this, right? And yeah, same warning with the return statement that we can ignore. And I am going to deploy calc v2 right now. So calc v2 is here, and we can see that it has the same functions, but I'm more interested in calc v2 address, right? So before we do that, let's try multiply, right? Multiply, say 3 by 5. The answer should be 15, but I actually get unsupported method. Now I'm going to copy calc v2 and set that as the implementation. That was successful. So now with my new implementation, if I call the exact same thing again, multiply with 3 and 5 as the parameters, I get the response of 15. Now let's try divide. And I'm going to divide, say, 19 by 6, right? So that will give me 3, and the reason for that is because the remainder gets discarded because we are dealing with, we're dealing with unsigned integers. There is no fractions or other sorts of things. So if you do 18 divided by 6 and 19 divided by 6, we'll get the same answer, 3, right? Because 19 divided by 6 is 3 and 1/3, I think, or 3 and 1/6, I think. Yep. So it basically is not going to go through. Okay, but let's try the other one, right? Let's try dividing by 0. 19 divided by 0, and no dice. The divide does not allow 0 divisor. All right, let's say this implementation is good and all, but for some reason we want to go back to the original implementation. Let's say this, implementation has a bug in it or something like that. So we can actually go back to the old implementation by copying the address and setting update implementation. Now to call divide, is now going to work again, unsupported method, right? So that means smart calculator, as long as you call update implementation with new addresses for new deployments of the implementations of that correspond to iCalc, it'll work fine. Now, there's one more thing which I haven't done, which is I guess out of scope, but I would normally do it in this circumstance. I would say EIP 165 require. So I would add a require statement to check that this address or new impl actually implements EIP 165 standard, which is to return a hash of its list of the iCalc function signatures, and that will basically mean that this is not some random address. It is an address that claims to implement iCalc, at least as far as you can figure out via the EIP 165 standard. So I would do that as well, but that's out of the scope of this, video. Okay, that's all for now. Thank you for watching.